But let's go over a quick review of what I think is important to know. Suppose you have a cloud of points, and let's say that there's two variables, x1 and x2, and this cloud of points essentially describes realizations of these two variables. So you might have an individual, you're measuring height and weight, and that would be x1 and x2, and then you just plot it on a plot. You might get measurements that look like that, or you might get measurements that look more like this. Okay, so each circle is a measurement, one single data point for those two unknown variables x1 and x2. Now, when we use multivariate Gaussians, we will essentially fit Gaussians to the data. The process of learning, in either the case on the left or the case on the right, is the process of fitting a Gaussian to those points. And hopefully that Gaussian describes those points. So for example, for these points here, I might want to choose a Gaussian that's centered at the origin, because they seem to be zero mean. And I might use some sort of covariance that is circular, because the points are sort of distributed in a circular way. Here they will be more like ellipses, and the mean will be a descent. The idea is that the mean, that is the location of the ellipse, and the size of the ellipse sort of describe the data. They're our model of the data. I'm going to refer to the center of this as the vector mu. Mu is a vector. It has two components because there's an x1, there's an x2. It's a point in 2D. Therefore, it must have two components. Now, it is also true that any of these points has two components, x1 and x2. So we can think of these points in the plane as vectors in 2D space. Okay. They can be negative, they can be positive. The real numbers, we often use this symbol belong to the real plane. So if you put a square, you can think of R is the real line, which is from minus infinity to infinity. If I square it, I'm getting the real plane, which is a plane, a sheet of paper that extends all the way to infinity. To say that something is Gaussian distributed is essentially saying that any point x1 and x2 comes from, that's what that tilde means, it comes from, or it's simulated from, or it's sampled from, all these are the same ways of saying the same thing. It's an example, any point there is an example of the kind of things you would expect to be within that red circle. And we say it's Gaussian. And we will say that it has, in this case, the mean is 0, 0, because it's centered at the origin. And now the question is, we need to talk about how are the points related to each other. So we need a concept that allows us to say, how does increasing x1 change x2? Are x1 and x2 related? So the variable that we use to describe that is correlation, or equivalently covariance. Okay. So in particular, there is a variable called correlation, sigma xy or x1, x2, which is just the covariance of x1 and x2 divided by the standard deviation of x1 times the standard deviation of x2. Now, what are all these quantities? The covariance is the term that goes inside, the covariances are the terms that go inside this matrix. Oops, you get a color. They are the expectations. In this case, we have a zero mean variable. And for this particular entry, the entry that should go in this cell is the expectation of x1 times x2. Sigma of x1 will be defined as the standard deviation, which is the square root of the variance, which is the square root of the expectation of x1 squared. If my mean wasn't 0, I would have to subtract 0. So this E, I'm using to denote the concept of expectation. The expectation is, think of the sample average, like if you toss a coin 1,000 times and you count how many times it's hit, as the number of coin tosses goes to infinity, you expect the number of heads to be a value. That is essentially what I mean by expected value. But now, the other thing that it's clear here is that the covariance, and by assuming the mean is 0, it's easier for me to make this argument, that the covariance is essentially the dot product of x1 and x2. Now, what happens when we take dot products of vectors? If you have a vector that looks like 1 and 0, and you dot product it times a vector that's 1 and 0, we get 1. Okay, so in the vector multiplication, first entry times first entry, second entry times second entry. However, if I have a vector that's 1, 0, and in this case, not the 1, 0 and 1, 0 are the same vector, so they're extremely similar. They're so similar that they are the same. But I could choose something that's very different to 1, 0, 0, 1. Now, they don't agree on the first coordinate, and they don't agree on the second coordinate. So when I take the dot product, I get 0. What can we conclude from this fact? We can conclude that dot products measure similarity. If 2 points are close by in 2D, if they're similar, their dot product will be higher. So the dot product is a measure of similarity. Now, that allows us to now go and decide what this covariance should be. Let's assume that this entry is 1 and this entry is 1, because let's just normalize so that the variances are 1. Then in this case, I would expect this to be 0. Okay. Because I can very easily pick a point in this cloud I can very easily pick 2 points in this cloud that have this property. Or put it another way, if I increase x1, suppose I increase x1 and I go here, then my chance of getting a point x2 that is positive or one that is negative is the same. by knowing something about x1, I don't know better about x2. So they're uncorrelated. Okay? Information about x1 does not help me gain more information about x2. If I know that x, on the other hand, contrasted to the case on the right. In this case, okay, let's go with the blue. In this case, if I pick a particular value of x1, this particular value, then I know that x2 will be positive with great probability. So knowing something about x1 tells me something about x2. So on the right, the points are correlated. The two variables are correlated. Knowing about x1 allows me to know something about x2. On the left, when the points are spherical, I don't have that information. If I do my Gaussian for this right-hand side, let's assume that I still have 1, but over here I'm not going to have 0. I'm going to have some positive number. That positive number basically indicates that if I expect x1 to increase, I should also expect x2 to increase. Whereas on the left, I'm saying that if I expect x1 to increase, I should not necessarily expect x2 to increase. Okay? That clear? Because that's a sort of what a Gaussian, what correlation is with random variables. So this is a property that we exploit throughout the course. It's essentially the basis of being able to do linear regression and nonlinear regression. So this is essentially what a multivariate Gaussian is. In this case, a bivariate Gaussian, because there's only 2 dimensions. But it allows us to see that if the entries of the covariance are 0, it means that variables are uncorrelated. Okay, so increasing one does not decrease the other. One does not depend on the other. If the entries are not 0, it means that one variable does depend on the other. And then they can depend in a positive way, or they can depend in a negative way, depending on your cloud of points. Okay. Now, let's illustrate now the Gaussian one more time. Let's assume we have some points. Again, we have x1 and x2. We have contour plots. And then this time I'm actually going to plot the Gaussian in 3D, which is this bell-shaped curve. Okay. This is essentially the distribution of x1 and x2. We call it the joint distribution, because it jointly models x1 and x2. In addition, I'm now going to do the following. I'm going to cut this Gaussian at a particular value. So I'm going to choose a particular value of x1. Okay, let's say this value here. Let's call it x1 with a in cursive. And I'm going to sort of cut a plane right through this Gaussian. So imagine you have a cake that looks like a bell, and you take a knife and you just cut it. Okay. Now imagine that you're this guy that's standing here on the side looking at your cut. What shape would you expect your cut to have? A Gaussian. So if you're looking at it from this angle, you would still quite likely expect to see a Gaussian that looks like this. Let's plot it. So you would be looking at x2, and you would be seeing a Gaussian that looks like this. That Gaussian is the probability of x2 given that x1, the variable x1, is that particular cursive, that particular slice. So when I write, and for short in the course, to avoid always defining the random variable, I often just write it this way. So this is a common practice in a lot of papers. But when you see that bar here, please do not ignore this bar, because this bar is so important. This bar gives us the semantics. Sometimes here there's a comma or not a comma. That's not very important. But that bar is important, because the moment you see x2 given x1, I'm talking about the distribution over x2. Whereas when I say x1 and x2, I'm talking about the 2D distribution of both x1 and x2. So they're two very different distributions, but one is obtained by cutting the other. Or we have a different way of talking about it in the language of statistics. We call it the cutting process. We call it conditioning. So this guy here goes by the name of the conditional distribution. Okay. Now, let us assume that the distribution of x1 and x2, the joint, is Gaussian with mean. The mean is the center. mu1 and mu2. And let's assume that it has a covariance that's sigma 1, 1, sigma 1, 2, sigma 2, 1, and sigma 2, 2. Okay. So that's our Gaussian that describes that cloud of points in that plot. Sigma 1, 2 and sigma 2, 1 are just a transpose of each other. And one of the properties that a covariance must have, so if you have a 1D variable, it wouldn't make sense to have a Gaussian, the sigma for a 1D Gaussian happens to be the width of the Gaussian. So the width has to be positive. It doesn't make sense to have a sort of a Gaussian that implodes on itself, that has negative variance. And so likewise for multivariate Gaussians, it doesn't make sense to have a Gaussian that implodes on itself. And so we require that covariance to be positive in some way. And that concept is what we call positive definiteness. So we require that matrix, the covariance matrix, to be symmetric, and we require its eigenvalues to be positive. That stops it from collapsing. In particular, we require that any arbitrary variable x times the covariance matrix has to be positive. So the exponent of a Gaussian has to be positive. A Gaussian is always e to a distance, and that distance has to be positive. That's what symmetric positive definiteness means. Okay. More important to our argument is the following thing. I might want to know what is the mean of this Gaussian, which I'm going to call it mu1, 2. I also might want to know what is the width of this Gaussian, which I will call sigma 1, 2. Wouldn't it be great if there was a formula that we could just read from the original model, given the original model, that we could just figure out mu1, 2 and sigma 1, 2? So think of the following setup. I have a cloud of points. We already know how to use maximum likelihood to fit a Gaussian to a cloud of points. We know how to estimate the mean. It's just the average. And we know how to estimate the variance as well, just by using the sample variance estimate. So we could obtain that red bell because we have all the tools that allows us to do it. But if I now ask you, give me the conditional, in other words, compute the green curve, how would you do it? Okay? That actually requires some work. It requires about 4 pages, perhaps a lot less, depending on how thrifty you are with your notation, of derivations. It's based on an idea called the short complement or the matrix inversion lemma. I'm not going to go over it in the course, okay, because it's a lot of algebra. If you are serious about machine learning, I strongly recommend you read chapter 4 of the textbook for the course, of Kevin Murphy's textbook, because he did a great job at putting in all the steps. But for now, let's assume that that theorem is given to us and will always be given to us. That theorem essentially tells us that mu1, 2 is equal to mu1 plus sigma 1, 2 times sigma 2, 2 minus 1 times x2 minus mu2. Where that x2 is that tilde x2 that we're conditioning on. Okay, so that formula exists. Moreover, there is also a formula that says that sigma 1, 2 is equal to sigma 1, 1 minus sigma 1, 2 times sigma 2, 2 minus 1 times sigma 2, 1. That essentially is what this theorem is saying from Kevin's book. The theorem says, consider a multivariate Gaussian. We're going to consider 2 blocks of that multivariate. So there's going to be a vector x1 and a vector x2. So far, because I've been plotting, I've assumed that x1 is scalar and x2 is scalar. But of course, the treatment is much more general. x1 could be a vector, x2 could be a vector. If you append 2 vectors, you still have a vector. And that vector is Gaussian distributed. Each vector component has a mean, mu1 and mu2. They have the same covariance that we've just went over in the drawing. And so the theorem essentially tells us what should the expression be for sigma 1, 2, and what should the expression be for sigma 2, sigma mu1, 2 and sigma 1, 2. The theorem is well within the reach of any grad student at UBC to go over the proof. In fact, if a grad student can go over that theorem, I think there's a problem as to whether you should be in grad school or not. But it's just tedious algebra, and there's no point in bore you with that algebra. What's important is for you to accept that such a theorem exists and to understand what the theorem does for you. The theorem simply allows you to go from a joint distribution to a conditional distribution. Okay, so if I give you a joint, if I tell you this is the covariance of the joint, this is the mean of the joint, you should be, and I ask you what's the conditional, you should be able to just apply that the equation, those 2 equations, to tell me what the conditional is. That's the value of the theorem. Okay. One more background thing about Gaussians. And this I've gone quickly over before in the course, but I think it's worth spending a bit more time on it. I'm going to do the following thing. I'm going to assume that we have a Gaussian variable a Gaussian distribution that we want to sample from. So now we're going to do the opposite process. Before, we had points and we were trying to figure out the curve. Now we're going to assume we have the curve. In other words, we have the mean and the variance, which is enough to plot the curve, to reconstruct the curve. And we're going to try to produce data. The motivation in learning for producing data is that if I can imagine the world and look at the world, and if what I see does not match what I imagine, it means that I need to update my knowledge. I need to learn, in other words, so that I can understand the world. So imagining is central to machine learning. And so I need to be able to draw samples from a Gaussian distribution. That's sort of one of the simplest things I could want to imagine. I will assume that I have a mechanism that produces uniform samples. Okay? So you have a random number generator that will give you numbers of equal probability between 0 and 1. That's what a uniform distribution is. I will also assume that I can compute the cumulative of a Gaussian. Now, what is the cumulative of a Gaussian? The cumulative of a Gaussian is what you get. Okay, so this is where mu is. The cumulative of a Gaussian is what you get if you start summing the area under the curve of the Gaussian as you move from the left. So all the way up to here, this area has a value. That value is the cumulative distribution. If I am to plot the cumulative over here, it would look like this. The inflection point, the point at which there's an inflection in the area, is the mean, right? Because the area to the left should be about the same as the area to the right, because the Gaussian is symmetric. I know this curve will go to 0. So one question for you guys. What is the asymptote of this curve? Is it 2? Is it 3? Is it pi? 1. Because the area under probability distribution is 1. Now, I've purposely drawn it like this so that I have my uniform distribution, which is between 0 and 1, produces numbers between 0 and 1 with equal probability. So it must be 1, 1 because the area of 1, 1 is 1 and the area under the probability must be 1. Now, if I can draw a random number from a uniform distribution, what I can do is I can project that number to the curve, and when it meets the curve, I project back, and I get a sample from the Gaussian. Right? This is how we sample. This is how you compute a sample, whether you use MATLAB or C or Python or whatever language you're using. They all use this technique called the inverse cumulative mapping. And then if you do this often, you will get something like this. You will get more samples in the middle, as you would expect, and less samples here. Less samples in the tail. So this is how we generate samples for a Gaussian distribution that has 0 means, or, well, in this case the mean wasn't 0, but typically we have a procedure in our computer that is capable of generating 0, 1 Gaussian variance. And essentially it uses the uniform distribution to be able to do that. Now let's assume that we're capable. And this process of sampling, I'm going to use the tilde to indicate. So a tilde, think of imagining. So I'm sampling a point I from a Gaussian that has mean 0 and variance 1. Now, if I want to imagine something from a Gaussian that has mean, I don't know, mu and some variance sigma squared, what I will do is I will just imagine a Gaussian that's 0, 1, because that's what I know how to do. And then I will multiply it times sigma. And the reason there's a sigma and a sigma squared is, remember that variance is the expectation of x times x. So it's an expectation of x squared. In fact, x minus the mu times x minus the mu. So x minus mu squared in the 1D case. If I multiply times a number, what I'm doing in terms of the expectation of that number squared is essentially squaring the variance. And of course, if I have a random signal and I just add to it a constant value, I just change its height. Okay, so adding a number mu is just changing the height. And now I have a way of drawing a random variable that has any mean or any variance. Okay. So that's the univariate case. In the multivariate case, suppose now that I have a vector with two variables, x1 and x2. How do I draw a vector from a Gaussian that is 0 mean and with covariance the identity matrix? That is, how do I now draw random vectors in 2D? To do this, we appeal to our theorem again. Oops. Our theorem also tells us that when you look at this Gaussian distribution, the multivariate Gaussian that has this variance sigma 1, 1 mu and mean mu 1, the marginal distribution just has mean mu 1 and sigma 1, 1. So to get the marginal for x1, you would just take the components mu 1 and sigma 1, 1. And to get the marginal for the other variable, you would take mu 2 and sigma 2, 2. In other words, what this equation is saying is that x1 by itself comes from a Gaussian that's 1D Gaussian that's 0, 1, and x2 comes from a 1D Gaussian that's 0, 1. They're not correlated because the off-diagonal elements are 0. That means that if we have the capability of drawing a random number, drawing 1D random variables that are Gaussian 0, 1, we also now have the capability of drawing vectors, because all we do is we append them. We draw each component. We draw x1 from a 1D Gaussian, 0, 1, and then we draw x2 from 1D Gaussian. And that's equivalent to drawing the vector x1, x2 from that Gaussian. Okay. Finally, if I want to now draw the vector x1, x2 from a multivariate Gaussian that has an arbitrary mean, mu1, mu2, and an arbitrary covariance, sigma 1, 1, sigma 2, 2, sigma 2, 1, sigma 1, 2. Let me call this matrix sigma, and let me call this vector mu for simplicity. Now, I don't have a way of taking, I need a way of taking square roots of matrices in order to be able to draw from this. Because essentially, I want to use the same trick. Let's call this vector x. I want to basically say that if x comes from a multivariate Gaussian with mean mu and covariance sigma, then x must be a sample from a multivariate Gaussian. Whoops, I went too quick. It would be nice to do exactly what we did for the 1D case. That is to write this as the mean plus some quantity times a Gaussian that's 0 and then identity. Okay. Okay? It would be great if we could do that. But for that, we need some sort of definition of what is the square root of a matrix. That definition is something that we get from linear algebra. And for your purposes, I don't need you to know what it is or how to derive it. If you're interested, just type it in Wikipedia and we'll tell you everything that you need to know about it. It's called the Cholesky decomposition. One of the most important algorithms ever invented. It basically says that you can take that matrix, sigma, and write it as a product of L of two matrices, one matrix and its transpose, LL transpose. So the Cholesky decomposition, it exists in any program, any programming language. There will be a function there that you can say, give me the Cholesky of a matrix. The way you compute the Cholesky is very similar to how you do LDU decomposition. So I don't know if you remember, like if you have a linear system of equations, we used to manipulate that linear system to map it into a lower triangular matrix, diagonal matrix, and an upper triangular. Cholesky's procedure is very similar to that. The point is we have that, and if we have that, now we have a way of drawing Gaussian distribution. We have a way of imagining Gaussian vectors for arbitrary means and arbitrary variances. That's the background. Now let's go back to regression. Let's assume now that we have x and f of x, and that our f of x is unknown, and we get data, and our objective is to learn f of x. We're trying to understand what is the function that describes the data. And so let's say that we have 3 data points. I will label those data points x1 with height f1. I should have drawn that a bit higher. x2, x3, and then I'm going to call this f2, and I'm going to call this height f3. Okay. Now, I'm going to assume that the x's are given. And that I want to model the f's. Okay. Moreover, I will assume that I want to model the f's with a multivariate Gaussian distribution. So I'm going to say, in particular, that f1 and f2 and f3, which are 3 numbers, form a vector. I'm going to assume that that vector, for simplicity, has 0 mean, okay, and that it has a covariance matrix, which I'm just going to call K11, K12, K13, K21, K31, K22, K32, K23, and K33. Okay? Now, what I will do next to is that covariance captures the correlation between those 3 points. If you look at those points, sort of x1 and x2 should be somewhat more correlated because they're nearby than x1 and x3. So I should expect that this covariance, let's say that the covariance is 1, the variances along the diagonal is 1. I should expect that x1 and x2 are a bit more correlated, perhaps. And so I would have here something like 0.7, 0.7. x1 and x3 are less correlated because they're far apart, so maybe I have here 0.2. And then x2 and x3 are also correlated, but just a little bit less. So let's say, for argument's sake, 0.6. The precise numbers don't matter. What matters is sort of the differences between them. Now, how could I construct a matrix that has this property? A matrix that says that F1 is highly correlated with F2, not so much correlated with F3. The way to do it is to let each element, Kij, be given by a measure of similarity. How do we construct a measure of similarity? There's many, many ways. One possible way is to use this quantity, which we call the squared exponential kernel. It's exponential and it's squaring a distance. Now, this guy here has the following properties. This guy here is 0 when the distance between xi and xj goes to infinity. Okay? E to the minus infinity is 0. E to the minus a large number is 1 over e to the a large number, which goes to 0. It will be 1 when xi is equal to xj. Okay? So in particular, that's why we get the 1s along the diagonal. So that function would allow me to get an SPD. I haven't proven it. There's a bit of math I could prove that this leads to an SPD matrix. But it certainly will give me a matrix that will have sort of that shape that I want, where I want points that are nearby to be more related to each other than points that are far apart from each other. And so if I were to fill the matrix using such a function, I would come up with a good model to describe that cloud of points, or at least describe their heights. I'm not intending to describe the x's. The x's are given. I'm only using the x's to construct k. Okay? The x's are used to construct k. But the distribution is over f, the height. Just like in linear regression, the distribution is over the y's, the height, not of the x. The x is an input that you're given, and then you need to make a prediction f. So if we want to capture similarity of points, we essentially use these similarity curves. Another fact is that if we have...
So if you wanted the points to be somewhat, like let's say that you wanted them to be dissimilar, right? And like where do you look up the function?
Let's first learn similarity, and then we'll deal with the similar. It's possible to modify the kernel to actually make points have different properties.
As a graduate student, and let's say you're trying to be good at this machine learning stuff, is one of your goals to know a bunch of these different functions just to kind of match whatever needs you have at the moment?
Yes, you will need to know some of these, but what we will also do is we will introduce parameters. And then the process of learning is figuring out those parameters. And we do that by maximum likelihood, for example. And so by learning the parameters of those functions, we will be able to change the kernel. We will be able to fit the kernel to the data. We'll be able to get kernels that gives us the most probable explanations of the data. But you are supposed to know if you do research on using Gaussian processes, it's good to know a few kernels. The squared exponential kernel is by far the one that's used the most. And but you could use different types of kernels. The Panernikov kernel, there's kernels that give you more jaggedy functions. There's kernels that give you periodic functions, and so on. So there's a whole family of kernels. And there are books written on kernels. There are entire books dedicated to kernels. There's kernels for text, there's kernels for images, and so on. I will just use the squared exponential kernel because my intent now is not to go and bombard you with all the things you could do. I first want to make sure that if I just give you one kernel, you know what to do. And once you know what to do with that kernel, we'll figure out what to do with the rest. Okay, let's proceed now to where things do get interesting. Okay, so we had our 3 points. Which I remind you were x1, f1. This is still f of x, and this is still x. I have x2, I have x3. But now, let's assume that I also have a point x star. Someone just gave me a point x star. And I do not know the height of that point. So the corresponding f, which I'm going to call f star, is a question mark, is unknown. I know my data D consists of my pairs x1 and f1, x2 and f2, and x3 and f3. That's my data. I've been given this. So I've been given the data. I've also been given an x star. Given these two things, I must answer this question. What is the height of f star? Should it be this? Should it be this? Should it be this? Should it be this? Let's put it to a vote. How many people think it should be the bottom triangle? The next one? The next triangle? The upper triangle. Okay, we have one vote for the upper triangle, so we'll shade it a bit. And so you seem to believe that this point is a good one. Now, what is why did we choose that point? We have to ask ourselves. And the reason why we chose it is because if this distance here is small, we somehow expect that the distances of that point to the points that are near it in terms of the heights will also be small. If I picked any of the other points, I would end up with a big distance. So it's a game of minimizing distances. This is what we call smoothness in machine learning. So for a small variation of the x's, you only want to see a small variation in the y's, or in the f's. Okay, so from before, if we go here, I knew that my f's were distributed according to a Gaussian, and I'm just going to say that the vector f, which is f1, f2, and f3, is distributed according to a Gaussian that has zero mean, so now this is sort of the vector of zeros, and covariance k. So I'm calling this matrix here k. Okay? So I know that f is distributed according to a Gaussian distribution in 3 dimensions, so a trivariate Gaussian that has mean 0 and has covariance k. I will also assume that f star comes from a Gaussian distribution which is also 0 mean. That's going to be my assumption. My assumption is I would expect the test data to come from the same distribution as the training data. It will have mean 0, and it will have a covariance which we're going to call k of x star. Well, actually the star should be at the bottom, but that doesn't matter. And x star. It's a self-covariance, in other words, the variance. So kx star, comma x star is just equal to e to the minus x star minus x star squared, which is just really 1, because x star minus x star is 0, e to the 0 is 1. Okay. Now f and f star by themselves are independent. I somehow want them to have the same property that all of you voted for. That is that they be correlated. That if you increase x, if by increasing f, can't get these x's and f's right. If you increase x, f seems to increase. So if you increase x star, f star should also increase. If you increase x, f star should also increase too. Because that's essentially why we picked that triangle. So I want them to be correlated. So I can't just have them as 2 independent Gaussians, but I must have them together as a 4 vector, a 4D vector, a 3D vector f, and a 1D vector f star, coming from a Gaussian distribution that's still 0 mean, but with a covariance that is first the covariance k, which is k11, k12, k13, k21, k31, k22, k33, and k23, and k32. And now I'm in 4 dimensions, so I also need to look at the correlation of 1 with star. And I have here the k star 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 star. And I'm using the notation that this is just what I'm calling k star 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 star, so that I can fit. And I'm also using the notation that k1 star is just equal to the similarity between x1 and x star. So I would have k2 star, k3 star, and here I have the transpose, which is k star 1, k star 2, k star 3. I'm going to group this block. This block is the matrix K. This block here I'm going to call the matrix or K star. And then this one, as already is there, is just K star star. And let's just lastly close the bracket. So now we have a joint distribution over f and f star. If I ask you to get me the conditional of f star given f, what do you do? How would you go about it? Just use the theorem. We have a multivariate Gaussian, a joint Gaussian. We want a conditional. We use the theorem. When f is given, that means you have a 4-dimensional Gaussian, and if you've done a cut in 3 dimensions. Those are the 3 points f. 3 cuts. And you're just left with a 1D Gaussian, and that's the Gaussian for x star. And so f in particular, if I using the theorem, f star is equal to k star transpose times big K minus 1 times the vector f. That's f star. That's the mean of f star. Which is, I'm going to say it's the expectation of f star, which is mu star. Okay. That will be most likely this height here, mu star. I also can use the theorem and get the covariance. It's sigma star, which is equal, using the theorem, I'm just reading it off here from my notes, it's just k star, k minus 1 times k star, and I need a transpose there, plus k star star. Oh, sorry, minus this plus k star star. What this sigma does is sorry about that, that sigma gives me the variance. That's what that sigma star gives me. So for any point now, I know where the mean, for any x star, I can predict where the mean should be, and I can predict what its, say, confidence intervals would be, say, a fifth times the variance, or whichever confidence interval you use. When you plot confidence intervals, you can just use the variances, or 2 times the variance. And then for a Gaussian, we have these rules that tell us what are the 95% confidence intervals and so on. So, in other words, for a point in the test set, I can predict the mean and the variance. Okay, so we have again x1, x2, x3. So I argued that for a point x star, I know its mean and variance, something like this. But now I can pick a different x star. If I choose another x star, let's say here, I would also get something that would look like this. And if I pick an x star here, I might get something that would look like this. Right? I could pick any x star. So, having derived the expression for the mean and the variance, I actually now have a general way of predicting for any x star. I just plug in the x star, I get the prediction, mu and sigma. So, in effect, if I take a large number of points, I can plot a beautiful line going through those points. That's just the mean. Each point in that line is the mean. In fact, I can use an infinite number of points. And here comes the Gaussian process idea. If I can do it for any point, in fact, I can do it for the function. Okay, what I have is a function that I put as input x star, I get as output the mean and the variance. It's a function. I also have a function that gives me these confidence intervals. Oops. If I connect the confidence intervals, let's use purple. Purple. If I connect these confidence intervals, I will get something that will look like this. So for any point x star, I can compute the confidence intervals and I can compute the mean. If my technique works well, I would expect the confidence intervals to look like that. In other words, where the data is, I have high confidence, so the uncertainty is low. When I don't have data, I can't be too confident. So as I try to extrapolate beyond where my data is, I should not be too confident of the predictions I'm getting. And this brings us to Gaussian processes. So we basically covered it, most of the preliminaries that allow us now to understand what Gaussian processes are doing. A Gaussian process is a distribution over functions. And it is over functions because the mean and the variance are just functions of x. For any x, I can tell you what the mean is. So there is a function. You pass x, it returns mu of x. There's another function called the kernel, because it's the function of two things. You pass x, any x, and any other x, which we call x prime in this drawing, and it returns k. It returns a scalar. So we have those two functions. If I have those two functions, what I can do is I can get a very fine grid of points. Very fine grid. So fine that when I plot it, it looks like a function, even though what I'm plotting there is a vector. And each color, each line there is a single vector. Okay? But because I've chosen my points x1 and x2 so close to each other, it looks like a function. So I create x1 to n. From x1 to n, I create mu. In this case, I've chosen mu to be the zero vector. So it's the zero vector with n entries. And I create a matrix K, which is n by n, which I create using this formula. So that 2 points are close by, they're most similar. 2 points that are far apart should be less similar. And after I've created this, I find what the Cholesky decomposition is of K. And then I draw a bunch of samples, FIs, which are samples from a Gaussian distribution that has mean 0n and covariance k. But the way I draw it is by drawing standard 0, 1 Gaussian variables and multiplying them times the matrix L, the square root of k, if you will. Just like we did before to generate Gaussian numbers. And what you see is this curve here is f1, this curve here is f2, and so on. In this plot here, n is equal to, I believe, 50. The code that I used to do this is this code. This code basically says that it's 50 points, n is 50. I then generate a regular grid of points for x. I compute the kernel matrix To compute the kernel, I just call this function called the kernel function, which you pass a and b, and it returns the value of the kernel. And it's this e to the minus squared distance. I then compute the Cholesky decomposition here. And then this operation here is just a sampling, L times N0I. And I draw 10 samples. And then I plot them. And that plot is that plot. Okay? So that's where those functions come from. And I'm saying functions because theoretically I could make this n go to infinity, the number of points go to infinity. So I could, in principle, draw functions. The only thing that's stopping me from working with functions is because engineers who still have not figured out how to build analog computers properly. That's the only thing. Computers have only existed properly. There are analog computers. Each of you has an analog computer in your head.
They also preceded digital computers.
Yes, I mean, this is an analog device. And there's other models that von Neumann came up with. Let's not go there. That's outside machine learning. Okay. Now, the process of making predictions is just like in the drawing. It's just like in this drawing here that we did before. If I want to make predictions, I'm going to have my points x, f, and then I'm going to try to generate the mean and confidence intervals elsewhere. In other words, given that I have the training data points, these points here, xi and fi, I will combine the data with my prior of the functions. And why is it a prior? It's a prior because I'm specifying via the covariance that I want my functions to be smooth. I've chosen a similarity matrix because I'm basically saying, hey, function approximator, when you fit my data, make sure that if 2 points are close by, that the heights are also close by. That is how I'm encoding prior knowledge. I'm encoding the prior knowledge that most things I see in the world seem to be of that nature. Let's just not pay only attention to the data, but let's also pay attention to things that seem to me common sense to describe the world. And if you do that, then, well, we get these fits. Now, this is actually also using that piece of code that I've shown you a snippet. And that piece of code was being distributed to you in the Google group, and it's also on the course website with the homework. Homework 2 is available on the course website. And if I were to draw functions from that Gaussian, I haven't told you what the mean is and the variance, but it's essentially the conditional Gaussian. We're going to play the same game. The joint is going to be f and f star. And then f star given f is just going to be a conditional Gaussian. I can evaluate that conditional Gaussian for any point. And that's what allows me to take a large number of points along the x direction. And for all those points, I can compute the mean. And for all those points, I can compute the confidence interval. And I get these beautiful plots that look like that. And fortunately, if I do what the theorem tells me, I get what I want. Where there's data, the variance is small. Where there isn't data, the variance is large. And if I were to draw samples from this Gaussian now, the samples would look like the bottom right figure. The data basically squishes the uncertainty. It grabs all those functions and ties them. By how much it does it depends on how noisy the data is. In this plot, the data is actually not very noisy at all, so we're seeing a good concentration of the functions, but we don't see this always, as we'll see later. Now, the confidence intervals of this nature are very useful because, as we know, if you know where you're uncertain, that's where you can query the next point to minimize your uncertainty. Okay. Now, let's just do what we've done with the drawing, but let's do it now a bit more formally. So, more formally, we have data, xi and fi, and we have n such data points. I'm going to assume that we don't have noise, so fi is just f of xi. We can actually, when we try an x, we actually get to observe the function. There's no noise in that observation. Now, given a bunch of test points x star, okay, we can assume that each of these points x star is itself a vector, because we might be trying to observe not just 1D quantities, but 2D quantities and so on. We want to compute f star. So it's the same game as before. We have x's. These x's are the input features. We have x stars, which is any arbitrary test point. We have the f's from the training data, and so the only unknown is the f stars. The x's are given, so we form the matrix K. We form the matrix K star, and form the matrix K star star. Once you have that, then you know that f and f star are a joint vector that comes from that multivariate Gaussian. As before, we use some kernel. And here you can see that I've started introducing parameters that change the kernel. And if you have that multivariate Gaussian, we use our theorem, we get the condition. And that's what I'm using to plot that. So for each point x star, I know the mean and I know the variance. If I have about 50 points here, and actually this plot was generated with 50 points, essentially what I'm showing you here is essentially for those 50 points chosen finely along this grid. For those 50 points, I'm plotting you the mean, mu star, and k star star. And sorry, sigma, the variance of these points. This guy here. So the sigma star is giving me this width, and this location here is mu star. And that's essentially why Gaussian processes work. So when we do Gaussian processes, we're essentially, all we're saying is, as the input, that we want 2 points whose x is nearby, 2 nearby x's, to have nearby f's. And that's all we're saying. And then we model all the f's with a Gaussian, because a Gaussian allows us to model similarity. And then for any other point that we add to this Gaussian, we can generate a much bigger Gaussian that's a multivariate joint Gaussian, f over f and f star. And then if I want to know what should be f star, for any x star, I just collapse by conditioning. So I take slice, and I look at, and I project. And again, I can draw functions. The kernel matters. So that's how we do Gaussian processes. So now I hope you look at the code, and you will see that the code essentially consists of those two formulas. I will spend next lecture going over Gaussian processes. I will finish this lecture next time. But, oops. I just want to give you some guidance in reading the code. Okay, I'll finish the lecture. We'll continue with this lecture on Tuesday. I've decided to throw some material out of the course and make the course go slower over the material to make sure that we can follow what's going on. Gaussian process is an extremely useful technique you can apply to everywhere, so it's worth spending your time. The code that I will give you computes Gaussian processes using Cholesky. So the mean prediction, F bar is usually to indicate the mean. Oops. We're going to finish the presentation, but what I'm going to tell you now is enough for you to understand the code. The code computes the mean. Now, naively, we could just use this formula. However, K tends to be poorly conditioned. So if we invert it, we get it into trouble. A numerical stable way of inverting K is to compute the Cholesky decomposition of K. And for now, ignore this Y here. I will explain the Y in the next lecture. Just think of it as our usual K. We're going to form the Cholesky. And from the Cholesky, we're going to call this guy alpha, K minus 1I. And so instead, we're going to use the inverse of the Cholesky, which is much more easy to compute. And then if I call this term M, if M is equal to L minus 1Y, then it must be that Lm is equal to Y. So in order to compute M, I solve a linear system of equations with matrix L and vector Y. That is essentially how I do the code. In the code, I compute the Cholesky decomposition of K, and then I solve a linear system, which in Python or MATLAB is just with this backslash operator. That gives me M. And then once you have M, you have another linear system, which is L minus transpose M, which you can call, I don't know, Q. And then you solve for Q. Oh, in fact, at that point is actually alpha. And then you solve that linear system of equation for alpha. So L transpose alpha is equal to M. And so that's how I'm computing this term alpha. Once I have alpha, I multiply it by K, and I get the expectation, which is just mu star. And the same trick is used for the variance. And that, in that many lines of code is the code for doing Gaussian processes. It's conceptually hard to get Gaussian processes because you're computing with functions and because we're no longer using our notions of calculus, but instead to get at it, we're getting at it from probability and priors. But once you're comfortable with the probability and you get to Gaussian processes, you realize that now you have a tool that can do any nonlinear regression. Like linear regression is actually not much easier than doing this, and it's so much more limited than this. This gives you good fits, this gives you confidence intervals, and this will be the basis to do a lot of very cool applications. Algorithm configuration, forecasting. It's Gaussian processes are used a lot. They're used in SIGGRAPH in animation. They're used all over the place. It's an extremely popular tool. All right, see you next week.